Hi. So today we continue with the new way to describe relations with parametric coordinates. So last time we had a little quiz. Let me do it. Exercise 5. I guess question was not really to solve the exercise the way the textbook wants it, but to just convert this to XY coordinates or rectangular coordinates instead of those parametric. And it looks like from my first equation, I can pull out the parameter t, which is going to be x minus 1, and then replace it into the second equation to get a relation on x and y. So x minus 1 squared will be our equation. So they also say sketch a graph here, so I can graph parabola that is shifted by 1 unit to the right, somehow like that. And that's definitely much faster way to do the work. Now, are there any restrictions when you're graphing? So the answer for the quiz is here. But are there any restrictions? Well, looks like they have second equation that deals with values for parameters squared, which means that y can only be positive, but that's what we experience in the graph of this parabola anyways. So looks like there is no other restriction is given to us, and Nesson arises automatically. So that's it. That's our graph for the exercise. So the graphing methods are definitely helpful, and we are going to work on these graphing ideas in the next section that actually designed to help us graph various relations, let's say like in the part D, for instance, where you have all kinds of special points such as maximum, minimum points, and also points where the derivative is undefined, right? When the derivative or slope of tangent line is undefined. And once you have these special points, then definitely can get a graph. And that's the plan for graphing in college algebra and Calc 1. And now we're going to utilize the same methods again in the calculus 2 by, first of all, studying derivative for parametric functions, which is not very obvious, turns out, expression. So derivative we used to write as dy over dx, and the way they define it is y prime divided by x prime of t. So you have two functions with respect to the parameter t, and you take derivative of first and divide by derivative of second. And that's how you get dy dx. And by the way, if you want to get dx dy, then you just flip this fraction, and that's going to be derivative with respect to variable y. So they do the justification of this simply by writing the two derivatives of y and x with respect to their definitions, and then they divide, and that's pretty much all it is. It's, I guess, very straightforward procedure. I guess I'd like to look at the example here that will show us the, well, kind of unusual setting for this derivative. So you really want to go through it and see how it works. So I can take derivative of function x, which is derivative of a function sine, which is cosine, right? And then derivative of y, which is derivative of cosine, which is negative sine. And then what you need to do to produce dy dx is divide one derivative by the other. And that's what I guess is kind of unusual thing. So you take y prime, which is negative sine, and you divide by x prime, which is cosine. You see, that's like we had derivatives of quotient. There was like derivative denominator squared y prime x minus x prime y. And well, here it's different. That's why I'm saying it's not something that we saw before. And one needs to kind of get used to setting these fractions. So you just find derivative of one piece, derivative of the other piece, and then divide one by the other. So people notice that this is tangent, sine over cosine, right? That's the tangent. Now, you can also find the second derivative by taking the derivative of the first piece. So if you call it as a d2 second derivative with respect to dx squared. So they call it as a second derivative. So they need to take a derivative of tangent. Remember, derivative of tangent, secant squared, something like that. And since it's a negative, so it'll be negative secant squared of t. And then you still have to divide this by that same exact x prime. That's what they have here in the definition. So they need to, again, put that cosine in denominator. So you set your derivative from ingredients, and you're always going to put that derivative of function x with respect to t in denominator. Secant is 1 over cosine, so this is going to be something like 1 over cosine cube, I guess. So it's worth to double check if you forgot the derivative of tangent is secant squared, or look at the first pages. Remember, in the first pages, that's where they actually have it. If you don't want to go through derivative of quotient again, let me double check. 746 is where we are. Point is, you have it all available, so you don't have to really memorize anything in here. So if you take a derivative of a secant, which is where arc sine, the secant derivative of tangent, where's the tangent? Do you see which number corresponds to it? Tangent. Here, 15, right? Secant squared. 15. So the point is, we have a nice reference page, so you don't need to worry. It takes no time to double check to make sure that you're doing it correctly. So first and second derivatives that we find, and of course the key idea is why we are doing it, and it's shown in examples, like in example 2 here is nice, deals with parabola. So it looks like the point of concern is vertex, right? The one on the bottom when derivative is equal to 0. And you can see when you find the derivative of this function, which is t to the power of 3 over 2, if you set it equal to 0, you see that happens when value of your parameter t is 0. So when t is 0, well, you plug 0, you get x, which is a square root of 0, means that x is 0. So it means that point is here, x 0. And then you can also find what y is, like negative 1, right? When you plug 0 here for x. So that's how we used to find critical points. We take derivative and set it equal to 0, and that's all it is. Well, in this example, they want you not to find the critical point. They want you to deal with point with coordinates 2 and 3 for some reason that actually corresponds to value of parameter t equal to 4, well, then if you plug it into your derivative, you will see that it should be positive. So dy dx at that point, t equal to 4 is 8. So slope of tangent line is 8. So we get a tangent line with positive slope. So whatever you can conclude from here. I guess our key idea is to see when derivative is 0. But of course, you can find some more points. So in the next example, analogously, you could find those special points where your derivative is equal to 0, and they also doing it here. I think they found derivative at least. And then you definitely want to see what happens when derivative is 0. So when you have dy over dx, when this derivative is equal to 0, it means that sine is 0, and sine is 0 when x is equal to 0. It looks like this happens at this particular point, right? When t is equal to 0, so you can see the coordinates of this point. So for x, it's going to be 0 because 0 minus 0, and for y, it's going to be something like 2 minus 1. So you get number 2 minus actually pi, so it's negative, right? Pi, it's 1.5, so it's somewhere here, the point where we have tangent line against horizontal. And that's graphing start. The other 2 points that could be interesting for graphing looks like where the derivative is not equal to 0, where actually denominator is 0, right? So you can set your denominator equal to 0 and find 2 other points. So cosine is equal to like 2 over pi. So you get some tedious numbers, but that's corresponding for x coordinates on the left and the right, where derivative is undefined. So I guess it's good to take an actual example and try to do this, and that will be a good way to practice with derivatives. So maybe I'll do it before I move to the arc length story, because that's another interesting part of this section. So let me take a look at some of the exercises and try to, I guess, examine function that we are given in terms of these parametric coordinates, and or maybe a relation, may not even be a function. So let me try to find those derivatives, like starting in exercise 5 and so forth, that wants us to get and first and second derivative. So let me try one. Let's say, how about exercise 8? Let's do something with polynomial setting first. So if your function x is t squared and 5t and 4, and then y is 4t. So you're given the curve parametrically. You can actually notice that if you pulled out from the second equation your parameter t, so like y over 4, and then plug it in for x, you're going to get parabola-like structure, the parabola that opens to the right or to the left, probably to the right. So that'd be not a function, but I'm talking about this curve that's probably in the shape of this type. But anyways, let us set those derivatives equal to 0. So dy dt, which is going to be a quotient of y prime with respect to t and x prime with respect to t. So take the y prime, which is 4, and x prime will be 2t minus 5. So that's our derivative. Notice it's never equal to 0. Please notice that this is like a parabola that opens to the right, so it doesn't have any minimums or maximum. It just keeps going upwards here and downwards there, so it doesn't have any asymptotes. But it has an issue here, and that's the issue point where my derivative is actually undefined, right? And when derivative is undefined? Well, when denominator is 0, right? So dy over dx, sorry. So denominator is 0, then dy over dx is undefined. Means that slope of tangent line does not exist, or it's a vertical line. So denominator is 0, so t is 5/2, and then we can 5/2, write it nice, or 2.5 if you wish. Oh, 2t plus 5. Thank you for noticing. That's very nice that you double checked, right? So it should be concentrated, and that it's plus. I don't know why I put minus. So it is going to be negative, right? 5/2. See, no wonder I made a miswriting. The pencil didn't want to write incorrect thing. So when t is equal to -π/2, so what is a point that we have here? Well, let's find its coordinates when t is -5/2 or 2.5, whatever you prefer to use. -2.5. So for y, I can get -2.5 times 4, which is -10. That's pretty straightforward. For x, it'd be a little bit less pleasant. So we can maybe just use a calculator. Would be a good idea. Why should I make another misprint, right? Get a scientific calculator and enter this t squared or 2.5 squared. I know it's with minus, but it's actually going to be a squared, so it doesn't matter. Then 5 times 2.5 and plus 4. So I got this other coordinates is -2.25. And this way I can actually have my graph produced, right? Because the point we have here is with coordinates -2.25 for x, and then -10 for y. And so my x-axis is going to be someplace here. So it's below, since y is -10 and x is somewhere. So this maybe kind of vertex of that parabola that opens to the right. So the ideas are same that we already went over before in the previous class, not in this class, but hopefully you are good at graphing, right? Using the vertices. And also one extra idea that I wanted to come across is when you actually have points where your tangent line is vertical. And those points appear when you have another function, right? When you have a relation, and that's why we need to work with zeros of denominator. That's something that is not very common in calculus because we usually work with functions, but from now on you will see these relations that are not functions and utilize those ideas. So we have the graph, and you could also find the second derivative because in this exercise they also ask for finding the second derivative, right? So how can I do that? d2y over dx squared. Well, I need to differentiate this stuff. Please notice that I would rather write it as a 4 times 2t plus 5 to the power of -1. so I can use the power rule for derivative rather than quotient, because quotient is really something I always want to avoid. So when the power rule is used, we get a -4, which is multiplied by this 2t plus 5 raised to the power of -1, subtract another one is -2. And then because of the chain rule, we also take a derivative of what's in the parentheses, right? So it'd be a derivative of 2t plus 5, which is 2. And then for denominator, I still have exact same as before, so I copy that 2t plus 5. It looks like you can do a little bit of algebra, like put -8 on the top, and on the bottom you have the 2t plus 5 raised to the power of 3. Well, looks like this is something that I guess called second derivative. I don't think I want to use it anywhere here, but we just found. So anyways, you can see that finding second derivatives sometimes could be tedious if you end up with a quotient or product. You have to use those rules. I could avoid it with this exercise because I rolled it as power of -1, but sometimes you can't, especially when you have a whole bunch of functions present. Then you end up, especially in the second derivative, with some tedious looking expressions. Other part of this section talks about old favorite length of arc formula that we can nicely modify with respect to the derivative of x and derivative of y. So I hope you recognize the formula for arc length. And what they do then is they work with this function the following way. So they already know that dy over dx is a fraction with respect to the t's. So it's dy dt. That's what we just did when we found our first derivative. And then dx dt. And then they do a little bit of algebraic manipulations. So they wrote it like that, squared. And what they actually are doing is finding the same denominator inside this radical, and then they factor out this denominator and end up with a canceling of dx over dt. And then they end up with this formula, which I like to write as a arc length, which is a square root extracted from y prime squared plus x prime squared. Or you could just write this as those function x prime squared. I think it's more compact, means the same thing, but I guess it's convenient when you use it in the exercises like that. And of course, it's going to be taken the integral with respect to variable t, because these are all derivatives with respect to t. And of course, starts someplace and ends also at someplace with respect to the parameter t. So that's another thing to realize. So now we only care about the parameter t, not with respect to x or y. And these exercises, they have their own specific. Remember, we need to work on the radicand first, because usually you can nicely simplify this as a perfect square, and so you can extract the square root. Let me try to find the arc length here for practice sake. Let me see where they have those arc length questions. Okay, start at 57. So let me try one, like maybe 57. I could take a look at. Looks like 57 does not have very nice looking function, but well, let us see what's gonna come out. So we have x given as a cosine cube theta, and then y is a times sine cube. Okay. Looks like there'll be a chain rule that will make things look not very nice, right? So let me do this. So y prime, derivative of the first one. A will stay. Now I need to take a derivative of cube. So 3 goes on the ground and sine will be squared. And then I need to take a derivative of function sine, which is a cosine. Look at this nasty expression. Now for the derivative of x, similarly, I also put a, the constant, and then multiply by 3 times. Now we have a cosine squared. Right? Now I'm differentiating the x coordinate. And then multiplied by derivative of cosine, which is a negative sign. Well, next step will be to get these two pieces added together. So what is y prime squared plus x prime squared? Well, let's see. They both gonna be positives, right? So I think that 3a, when I square, I get 9a squared. So I'll be able to factor this out. And then inside the parentheses, I'm gonna have a sine to the 4th multiplied by cosine squared. You can put thetas, but it's just, let's put thetas. And then that's for my y prime squared that I need to add with the x prime squared. So that's also 9a to the 2nd power. And now we have a cosine raised to the power of 4 and the sine squared. So it looks like I want to factor something out because the goal is to come up with a square root. So we want to definitely perfect square inside the square root. It's always the case with the arc length. So I can see that 9a to the 2nd is a perfect square that I can take out. It looks like sine squared and cosine squared. I can also factor it out. That's good. So what's left? Well, from the first, we'll have a square of sine. And from the second, we will have a square of cosine. How about that? It's equal to 1, right? So that makes me feel real good because I like when they get compact. So since this is 1, then now I can actually set up this integral, right? So let me get room for this. So arc length problems are pretty tedious. I would say you can do one of them. That should be good enough. Because if you know how to do one, they're all same. But you might end up with various tedious antiderivatives at the end, because integration of those trig functions may give you a little bit of hard time. But anyways, so the arc length is going to be integrating. Now, the parameter varies from 0 to 2 pi. Okay. Looks like it's same for all of them. Parameter is theta, so standard. And then we need to extract the square root from this stuff, which is a perfect square, and that's pretty nice. It's 9a squared sine cosine. So how would you take the antiderivative when you extract the square root? Well, it looks like you can either substitute sine or cosine, whichever you prefer. So you're gonna get, maybe I put 3a on the outside because it's a constant. So I don't want to bother with that stuff. And then sine, cosine. So if I, let's say, substitute cosine, if I substitute sine, better do sine, right? Then its derivative will be cosine times d theta, of course, is du. And that just went through perfectly fine. So we end up with still that same 3a, and then the sine is going to be u, and cosine theta d theta is our du. How about that? That's nice, because sometimes you do get something not very attractive. But anyways, u squared over 2, and that's definite integral. So I go back with my original variable. So that's going to be sine theta from 0 to 2 pi. Whether you like to get new parameters or not is your choice, because you're always going to have same answer. Right? So sine of 2 pi minus sine of 0. I say, is that going to be 0? The sine of 2 pi is also 0. Well, looks like that's what they have. So when you say is arc length really going to be a 0 for this curve, so how come it's actually a 0? Because we have sine of 2 pi, right? Remember? That's kind of odd, right? So you can figure out what happened, because at 2 pi and at 0, our function sine has value equal to 0, right? And that's a little bit concerning, well, you say, Alex, because you're not careful here. You have u squared over 2, so sine squared has to be here. Oh, okay. But still, if I plug in the 2 pi, I get a 0, right? And 0, I still have a 0. So how come it's 0? So that's definitely something not right, because again, it's an arc length. So why is it 0? Well, could be interesting to think about. In fact, it could be, oh, what is a? Well, a could be any number. That's, you can put 1 or 2 or something. So that's some kind of constant that they have here. So notice it's still the same thing. My concern right now is with the 0 that we produce. Actually, they don't ask, we just found the answer, but I kind of concerned with this answer, because it shouldn't be 0, because arc length should be some kind of length, right? Maybe what you can do is get a 0 to pi, and then from pi to 2 pi, so there's 2 pieces, and then add them together. How would you know that? Well, you probably should graph it, but they don't ask you to do the graphing, and I can actually try to graph it using some technology. I'm not sure if Desmos is gonna be useful here. Let me try to see if I can graph parametric. Parametric graph. Interesting. Do they have in this Desmos? Yeah, let's try Desmos. I think Desmos is nice tool. Is it actually? No, I think I'll start wasting time, because it looks like I'm not sure. I know there should be graphing for parametric functions. You can try one of those and graph and tell me next time how it came out. Because again, it should be some free calculator available. Well, my concern right now is not with this. My concern is with actually finding derivatives. And that's the key idea. So you get this derivatives, and then you divide one by the other, like we did already in one of the exercises. So I'd like to do another one, and maybe you can try one as well. How about that? Let me try another derivative with the trig setting, maybe exercise number 9 for practice. And then I'll ask you to do something nice. Maybe I'll ask you for exercise number 7. That could be a fair exercise, I think. But anyways, let me try number 10. Again, I want to find first derivative, and I'll also find a second derivative. Why not? I'm sure this is something that you already know how to do this. You've been looking for tons and tons of derivatives. Now it just looks a little extra, right? With little extra added to the story. You need to, at the end of the day, simply divide one by the other. That's really all it is. So x is cosine and y is 3 times sine theta. What kind of figure is that? Probably it's ellipse, right? So 3 is for y is like 3 times longer than it's wider. But anyways, let us get x prime and y prime. And then I'll find dy over dx by setting this y prime over x prime. And both of them will be with respect to my parameter. In this case, it's called theta. Okay, whatever they call it, it's fine. So derivative of cosine is negative sine. And then derivative of 3 sine will be 3 times cosine. That's nice, pretty straightforward. So we have a 3 cosine divided by negative sine of theta. The sine over sine is cotangent, so it's minus 3 cotangent. Okay. So I found first derivative. That's what I'll ask you for a quiz. But I also want to find the second derivative, so that's called d2y dx squared. So we kind of have dx and then another dx in denominator because we already had one, and then we'll have another one. That's how they probably put dx squared. Instead of doing this, they just write it as dx squared. But anyways, let us take derivative of cotangent. So derivative of tangent was secant, so of cotangent is going to be cosecant squared. And they are multiplied. So that's my derivative of the top, and I need to put again this same x prime on the bottom, minus sine. So it looks like there are so many minuses, they will leave me with one negative only. So it'd be minus 3. Now cosecant is over sine, so it'd be, looks like sine squared coming from cosecant and another sine, so it'll be sine cubed. And this is it. So it looks like they're not that bad, these exercises. Again, we just want to get used to this. So the question for you, how about if you can please write what dy over dx is in the exercise number 7 for a little quiz. So exercise number 7, just write dy over dx. You don't have to plug value of parameter. You can see they have t here, something. No, you don't have to worry about this. So just dy over dx, and that's good. enough for today's little quiz, and then you can have a good weekend. So I hope you will enjoy it, and then we'll continue with the next section, which is going to be another familiar stuff. It'd be story of the so-called polar coordinates, the ones that we heavily used in trigonometry class. So little quiz, please. Take your time. Don't hurry.